5.2 is the other section that we're going to do that deals with complex numbers. This is DeMoivre's theorem. DeMoivre's theorem starts with the idea of what complex numbers look like on a graph, and then eventually it's going to end with what happens when we take like square roots or cube roots or fourth roots of complex numbers. Okay, so we looked at what happens when we did powers of complex numbers last time, right? That's what 5.1 was. And we're going to do essentially the opposite in 5.2. We're going to take radicals of complex numbers. All right, so here's the leading idea. DeMoivre's theorem shows us how to raise complex numbers to powers, or specifically, find roots. That's what I was referencing. By connecting algebra and trigonometry through a simple but powerful formula. It might seem complicated, but the theorem helps us solve problems that look impossible at first. Faith in God's similar. Sometimes life's challenges feel overwhelming, but trusting God's power and plan, even when it seems complex or beyond understanding, helps us overcome difficulties. Just as DeMoivre's theorem simplifies complex calculations, faith simplifies our trust in God's guidance through every challenge. So let's take a look at what a graph looks like so that we can establish how all of this connects together. When we're looking at a number, a plus bi, complex number, the way that this looks like on a graph is the following. So draw your standard XY graph. But the difference is this. Our x-axis is the real number axis, and our y-axis is the imaginary component axis. Okay, we talked about different dimensions last time, right? This is the idea. One of the dimensions is a horizontal dimension graphically, and the other dimension is a vertical dimension graphically, just like an XY pair would be. And this component right here will tell you how far you are over, if you will, on the real axis. And this component B tells you where you are on the imaginary axis. I'm assuming that the A and B in this case are both positive. Certainly wouldn't have to be, but this would be the location of A plus BI. Okay, now that kind of looks like vectors, doesn't it? Kind of looks like what we did with vectors as well. We had the I component and the J component. So there's connections throughout. That's purposeful. I mean, that's how the trigonometry is connecting with these two concepts. And then you see something else that looks very familiar. You see a formula that you've seen before with vectors. It's the absolute value. We called it magnitude when we did vectors. The absolute value of a complex number. And the absolute value of the complex number z, which we're calling a plus bi in its component form, is the absolute value of z, or absolute value of a plus bi, is the square root of a squared plus b squared. That's magnitude, right? At least when we're referencing vectors. It's also the Pythagorean theorem and the distance formula. All of it is interconnected. It's crazy, right? Yeah, so the trig is what allows us to connect all these things together. We're working at this from a trigonometric perspective. So the first thing we're going to take a look at then is how we graph, like we're going to do a couple of graphs, and finding the absolute value of these numbers. And this is our formula for doing so. And I'll establish as well why that actually makes sense when we do one. You can see it. All right, so our first one is just 3i. So we're going to draw our coordinate axis, right? The real axis, I won't label them, but the real axis is horizontal, the imaginary axis is vertical. What is the real number component if z is equal to 3i? It's 0. So there's an understood 0 plus, oh, sorry about that, change my pen. 0 plus in front of the 3i, true? Yeah, there's there. So there is no real number component. It does not move left or right on the horizontal axis. But there is an imaginary component. It's the number 3, right? The number in front of the I is 3. So what it tells us is that we're going to go up 3 on the imaginary axis. And this right here is our location in the complex number plane. There's no arrows like there were in vectors. That's not what we're doing, right? This is just a point. It is a point in the coordinate plane. That's the complex plane. Now, what is absolute value? Well, when we look at absolute value in the sense of just a number, like if you say the absolute value of 5, the answer is 5. And if I say the absolute value of -5, the answer is 5. And the reason is because it's measuring the distance back to 0 on a number line, right? So wherever you are on the number line, on the positive side or on the negative side, distance is positive and it puts you back down to the number 0. Takes you back. The same thing's happening here. This is the distance, but it's not to 0, at least not on a number line. It's to 0 in the coordinate plane, or the origin. So this right here is the origin, right? You can tell me without any calculations, though we will do the calculations in a moment, what is the distance from this location back to the origin? It's 3, right? Of course it is. There's actually no left and right to have to deal with. It's straight down. It's a distance of 3. So the absolute value of this is going to be 3. Now, from the perspective of that formula, what we're doing is taking the real number component and squaring it, the imaginary number component and squaring it, right? This gives me 9, and the square root of 9 is 3. So the formula still works, it's just not really necessary because there's only one component I'm dealing with. Okay? The next one's got the 2 components, so we're going to have more to do. Let's graph it first. Okay, so where am I going to be with the number -3 minus 4i? Let's talk quadrants. We've got that terminology. What quadrant will I be in? Quadrant 3, right? So the first component, -3, is the real number component. It tells me to go left 3. The second component, -4i, tells me to go down 4, like this, I. So this is -4i. This is -3, excuse me, if you want to label them that way instead of not having them labeled the way I hadn't before. And this right here would be my point. Okay, so this point right here is the point -3 minus 4i. Okay, everybody good with that? Now, what we're measuring, I'll draw it in a different color then, when we measure absolute value, is this distance back to 0. True? Do you see a triangle? It's not drawn in, but do you see where it could be drawn in? So if I were to draw this in a triangle perspective, you could draw it like that. You could also draw it over to the x-axis or the y-axis instead if you wanted, but yes, sir. Oh, you're good. You're good though. Okay, cool. So we see a triangle, right? We see a triangle with a side length of 3 right here and 4 right here. What's the third side of that triangle? It's 5. 3, 4, 5 is one of our Pythagorean triples. If you don't recognize it, that's fine. You can make the calculation. This is the square root of the first component squared, so it's -3 squared, plus the second component squared, which is -4 squared. Negatives, of course, cancel. 3 squared is 9, 4 squared is 16. It's almost like I've done this problem today. Square root of 9 plus 16 would be square root of 25, or 5. The absolute value is 5. Now, does the absolute value have to be a whole number? Of course not. It could be a radical form. That's fine. But notice it is always going to be positive. Distances, right? So we're calculating, we've calculated absolute values are always positive. And this calculation is always going to be positive because I've got the principal square root of positive things that are added underneath the radical. Okay? So we end up getting 5. All right. So the next thing we're going to take a look at is going to feel a little funny. So just bear with me so we can establish the definition, and then we'll get to what we're doing with it, okay? This is called polar form. So the polar form of a complex number, z equals a plus bi, is written as z equals r times cosine theta plus I sine theta, where a is equal to r cosine theta and b is equal to r sine theta. R is the square root of a squared plus b squared. The tangent of theta is b over a. R is called the modulus. That angle theta is called the argument. And the angle theta is between 0 and 2 pi. It looks awful, but it's actually all stuff you know. I'm going to show you why you know it. but this is all compacted into one definition with it together. So let's take a look at why it is you know this. We're going to draw where a plus bi is. In the coordinate plane. So this is where we said was a plus bi, correct? Everybody true, good so far? Okay. So this length right here is r. Okay, that's what it's defined to be r. Think about like the radius of a circle, right? Unit circle kind of stuff, but it's not a unit. How do I find that r? Well, that's exactly what I just described a moment ago is the absolute value. It's the square root of a squared plus b squared. And if we drew in the triangle, we would definitely be able to see that that is in fact a and b, and a squared plus b squared is r squared. Okay, so that takes care of this equation and where it came from. It's not anything new. What about the other components? Well, the theta that it's referring to is right here. Okay, everybody good? That's the angle. The argument is what they're calling it. That angle or that argument can relate the sides together. So check it out. If I wanted to find out the cosine of that angle, let's just do cosine. Looking at the side lengths A, B, and R, what is the cosine of that angle? Back to chapters 1 and 2. A over R. Cosine is adjacent over hypotenuse. It is A over R. Y'all good with that? Now notice what happens if I multiply the R to the other side. I get R cosine theta equals to A, and that's exactly what they told me right here. They're just establishing the relationship between these side lengths and this angle measure that's showing up when I put this into the complex numbers plane. The same thing happens, I won't belabor the point, but the same thing happens if I do sine of theta. If I do sine of theta, I get B over R, and it creates this formula. And if I get tangent of theta, I get opposite over adjacent, that's the B over A, so that's this formula or this equation, right? So all of these equations are coming out of the fact that I've got a triangle there, and there's an angle there, and I have sides and opposites and hypotenuses and such, and it all pieces together exactly like we've seen before. But it looks kind of funky. Agreed? The part that's new is the way that this is actually written here. Okay, that's what we're going to basically be practicing with. We could see where the thetas are coming from. We can see where the r is coming from. We're going to change the form a plus bi into this form r times cosine of theta plus I sine of theta. And with good reason, though right now it seems sort of like, why would we want to ever do that? Okay, we'll see the why. But are we good? Okay, so far. At least as good as we can be. Okay. So let's see a little bit of where this is headed then. We're going to take the same kind of thing we had before where we're plotting the coordinate and we're finding its polar form. So we have our number line, or not a number line, but our complex plane. Whoops, one more time. There we go. Where is -4 located? Real number on which side, Isaac?
Left side.
On the left side, you bet. It's the real number on the left side. So if I go 1, 2, 3, 4, roughly speaking, I'm right here, correct? Everybody good with that? Okay, so I'm supposed to now be writing this in r cosine theta plus I sine theta form. That's the goal. R, remember, measures the distance back to the origin. What is the distance from my point to the origin? It is 4, right? This is R. R's 4. Theta is supposed to be measuring the angle right here. You'll be happy to know we're going to work with degrees. Most of you like degrees a little bit better than radians. What angle measure is this in terms of degrees? 180. So this is 180, and this is 180. Okay, we're going to do it in radians in here in a second, but let's actually fill in what this says in terms of degrees. Z equals 4 cosine, of 180 plus I sine of 180. It still is not obvious why we would want to do this, but the pieces themselves were not hard to find, true? What if I had done this in radians? Because it does say degrees or radians, so let's just see what it looks like if you did it in radians. Well, you'd still have 4 and you'd still have cosine. What's this angle measure up here in terms of radians? It's pi. So instead of having 180s, we would have cosine of pi plus I sine of pi. Okay? We can do it. We just don't know why. Okay, let's try another one. This one actually has 2 components, though, instead of just being the -4 like the last one.
Is that just the whole answer?
Yes. All we're doing is to plot the number and then write the number in complex form. That's the only part of this direction right now. Okay, we haven't done anything with them or seen why we would ever want to do this at this point. We're just learning how to rewrite them. Right? Baby steps. Got to do one thing at a time. All right, this next one, a little bit of a step further because we're not just at the negative real axis. So as we look at this one, which quadrant am I in on this one? 1. I'm in quadrant 1, right? Both components are positive. So I've got the value of, and I don't need to necessarily draw this in a real number or in a, I don't want to, that's not the word I want, in like scaled form, but if it helps you to see it, I will. So the number 1, of course, on the real number side is right here. Okay. And then if I were to mark it out up here, the number square root of 3 is roughly in between 1 and 2. So square root of 3 is somewhere in here. So this number is right there, roughly speaking. So now we're going to find R. How do we find R? Well, it's a triangle, right? The height of the triangle is square root of 3. The width of the triangle is 1. I don't know if you can call it width, but the base of the triangle is 1. How do I find the third side? It's not 4, but you're close. It's not a triplet either, but it is a familiar value to you guys. Okay, so if it weren't familiar at all, what would we do? Pythagorean theorem. Okay, let's do the Pythagorean theorem and then you'll see why this is familiar. Okay, so let's find this side. We're going to call it R because that's what we're looking for anyway. So we have 1 squared plus square root of 3 squared equals R squared. So this is 1 plus 3 equals R squared, or 4. That's the 4 you were looking at, Braden, but what did we still need to do? Square root. There you go. So this R is equal to the square root, not square root, excuse me, is equal to 2. The reason that's a familiar triangle to us is because it's a 1 square root of 3, 2 triangle, it's a 30, 60, 90. We've seen this triangle before. It's the unit circle value. Okay, so that's where you've seen it. So it's not a Pythagorean triple because those are whole number values and these are not whole numbers. Square root of 3 is not a whole number. But it is definitely a common triangle that we've worked with. Okay, so our R is 2. So as we're taking a look at writing this in R cosine of theta plus I sine of theta form, the R is 2. Okay, now it is a familiar angle to us, but let's figure out what it is in case we weren't familiar with the angle. Remind you how you do it. The way that you get the angle is using the formula tangent of theta equals A over B. That's one of the 4 equations or whatever it was inside of the definition. We know what A and B are. A is the square root of 3 and B is 1. Right, here's my angle theta that I'm referencing here. Tangent is opposite over adjacent. So tangent of theta, opposite square root 3, that's a terrible 3, over 1. Okay, If you take your calculator, put it in degree mode so it'll be helpful, and you were to do the inverse tangent, right, of square root of 3, because square root of 3 over 1 is square root of 3, it's going to give you an angle measure for theta. And it's a familiar number. If it weren't a familiar number, you could still use it, right? Like, that'd be great. If it's like 42.7, great, we write down 42.7 degrees. This one is a familiar angle measure. Do you know which one this one is?
60.
This one is 60. Okay, and if you don't know, your calculator will tell you. It's fine, okay? But this is the the 60 degree angle on our unit circle. So this is 2 cosine of 60 plus I sine of 60. If we were specifically asked to do this in radians, it's possibly still nice enough to go through degrees to do that. So what is the radian measure for 60 degrees? Pi over 3. That is the radian measure. And if it were an ugly number like 42.7 degrees, you could still turn it into radians, right? You'd just multiply it by pi over 180, and it would be an ugly decimal number, right? It'd be something like 4.6 or 0.32 or something like that, and that's the number you'd put in that space instead of something with pi in it. That's okay. That's possible. Okay. How are we doing? Nobody's talking to me. So far, so good? Okay, right now we're just looking at a picture and we're turning it into angle measures. This all should be connecting to things we've done before. It's part of the reason why I really like this section is because it kind of draws us back into things that we've been working with from earlier. So we've been talking about polar form, right? That's what this is called. This is the definition from above. It says, nope, not that one. That one, there it is. This is the polar form of a complex number. Okay, this one right here. When it's written in this form right here, it has another name as well. This is called the rectangular form. Okay, so polar form is where we see the cosine and the sine and the theta. That's polar form. Okay, rectangular form is where it's written where we see the components individually. We see the real component, we see the imaginary component with the I attached. We see that that's rectangular component or form. So when this problem here asks us to write it in rectangular form, what it means is it wants us to take this and to turn it back into a plus bi. That's the goal. Okay? But here's the deal. Your calculator will help you with that, or in this case, your unit circle will, because this is a unit circle value. So, unit circle wise, put your unit circle hat back on. Man, 210. Where in the world is 210? Y'all remember? Where is 210? What quadrant am I in if I'm at 210? I'm in quadrant 3. Good. So I'm down here in quadrant 3 if I'm at 210. Y'all good? Okay. So if I'm at 210, what is this ordered pair? You're thinking about angle measure. I want the ordered pair, like the XY. Nope, but that would be the ones that are like that would be 225 in that quadrant. Okay, so this one's going to be a square root 3 over 2 and a 1/2. Let's make sure we get them in the right order. So somebody help me. Which one's first? Yeah, square root of 3 over 2 is the first one, and the second one's 1/2. Okay? They are both negative. Thanks for observing that. You betcha. Okay, all good? All right, so cosine is the x value. You remember that? Cosine is x. Sine is y. So the x, the part that's listed first, goes in first. That's convenient. Negative square root 3 over 2. And then we have our I. And then the y component goes in second. It's negative 1/2. The 4 will distribute, right? So when I take 4 times square root 3 over 2, well, it's still negative. What do I get? Four over 2 is 2. Thank you. This will give me a 2 square root 3. right? This 4 will reduce with this 2 to give me a 2, so I have 2 square root 3, and it's still negative. The I and the 1/2 will also be a negative, because there's that in the beginning. What happens when I multiply 4 by 1/2? I actually get 2 this time, and I'll put it as 2i, since I've got don't have any radicals involved. I'll just move that 2 to the beginning. This would be the rectangular form. Now, does that make sense? Does it look reasonable if I go negative 2 square root of 3 along the x-axis or the horizontal axis, and if I go down negative 2, right, because that's the I component, the imaginary component, I'm still in quadrant 3. It's a reasonable answer for what I'm looking at, true? It is, and it is the correct one too.
So with rectangular, you go to the unit circle.
You go to the unit circle, exactly. Let's write down the next definition, and then I will stop because we don't have time for the actual formula, the actual problems with it. This tells us what happens and why it's helpful in order for us to be able to use polar form instead of rectangular form for multiplication. So if we are wanting to multiply two polar formed complex numbers, R1 cosine theta 1 plus I sine theta 1, and R2 cosine theta 2 plus I sine theta 2. Okay, so this would be essentially multiplying like A plus BI times C plus DI. That's what we're doing. We're multiplying together. Now, if we did that, A plus BI and C plus DI, we would have to FOIL. We would have to combine pieces together. We would have to simplify the fact that the square root of or the I squared is -1. We'd have all that to do, right? Like we could do that. But this is actually a lot easier. Here's what it says we do when we multiply these. We multiply the real components in front. R1 and R2, they get multiplied. And we add the angles. There's no foiling. There's no combining like terms. You're just multiplying the numbers in front, adding the angles together underneath. And it will arrive at the exact same value as the other one would. Now, while we won't do it, let me show you what it looks like, and then I'll pick up with that as a posted video, right? So when I multiply these as Z1 times Z2, I will multiply these numbers together. That's easy. And I will add these numbers together. The fractions, we may not like it, but that's doable as well. And then the problem is done. It's a multiplication and an addition step. It's very quick. Okay? Yeah, but they'll be the same. Notice they're the same angles, so it'll show up twice. Yeah. Okay, so I'll pick up with the video I post with question number 6.